So these are Lewis electron dot configuration. So this is how we're going to start drawing our Lewis structures. So this is basically using the valence electrons off the periodic table. I'm trying to get a handout in a minute. Do you have this handout already?
Yes. But can I have another one?
It's the one
that more notes.
Yeah. So it's the drawing Lewis structures. We're not doing this yet, but that's what we're going to build up to. So what a Lewis electron dot configuration is, it's just a configuration using the symbol of the element and dots representing the valence electrons. Because what we're going to use these for is to show the structure of a compound as a whole. And when we're showing structure, valence electrons are the only electrons involved in those structures, because those are the ones that are involved in bonding, that outer shell. So let's just do some examples of it. So what do I have? Phosphorus, bromine, boron. So these are just the elements, symbols themselves. So if I wanted to represent these as Lewis electron dot configurations, what I would do is I would look at the periodic table, so starting with phosphorus, and based off where phosphorus is, how many valence electrons does it have?
5.
It has 5. It's in row 15, so it has 5 valence electrons. So what I'm going to do is I'm going to write the symbol for phosphorus, and I'm going to put 5 dots representing those electrons around phosphorus. Now when we do this, it's kind of like when we did those electron maps that we filled up, the orbital diagrams. You want to make sure to have just one electron on all 4 sides before you pair them. Okay, so you don't want to pair electrons if you have to. Since we have 5, we are going to have one pair, but the other 3 electrons should be on separate sides. So what I mean by that is this would be incorrect, because I'm pairing an electron when I don't have to. Because you're imagining a box around here. And you want to make sure that you don't have more than 2 electrons on each side of that box. And you don't want to pair the electrons, so you don't want to have 2 on a side if you don't have to. So the correct would be this. And it doesn't matter. So I have my pair on top. You could have maybe had your pair over here. That part doesn't matter, as long as you only have paired up one set on one side. All right, so let's do another one. Let's look at bromine. So in order to write its Lewis electron dot configuration, we need to know how many valence electrons. We go to the periodic table. It's a halogen. 7. So now we put 7 around bromine. And if you want, you can draw the box to help you. But I put 1, 1, 1, 1. I only have 4, so I have to pair. And I'm pairing almost all of them, right? I only have 1 unpaired. So my correct one would be this guy here. And I want to point out, this is going to help you. So the number of unpaired dots, that's how many electrons that element wants when you're looking at the nonmetals. So what I mean by that, we have a pair, and then we have these 3 that aren't paired, right? So that means phosphorus, to be happy, to have its full octet, it wants all of them paired, so it's going to want 3 more. And when it gains those 3 more, it forms a -3. So it's kind of bringing the charges and oxidation states back into it. So this bromine has 7, so it has 1 unpaired. It wants all of them to be paired to be happy. So if it gains 1 more, it's going to be bromine with a -1 charge. So it'll have an extra electron. Just to kind of bring it full circle. But we'll also see these in covalent bonds. So this unpaired electron, it might share instead and form a covalent bond instead of being an ion. So we're using this knowledge because we're going to bring it into actually pairing these up to make bonds. But before we do that, let's try one more.
3.
Bromine's got 3. And so when you draw it, bromine boron, you want just one on each side, so you're not pairing any. All right. So questions on how to come up with the Lewis dots, or how to figure out the valence electrons. Okay, so what we're going to practice next is just counting valence electrons, because that's our total, that's the first step when we're drawing Lewis structures. So when we take these and start bonding these atoms together, we need to know how many total valence electrons are in the compound that we're trying to draw. So that's what we're going to look at next. So we're going to count valence electrons. So counting them, I have a few examples. So I'm just going to put up some chemical compounds, chemical formulas, and we're going to count. Oops. Sorry. And then so if I wanted to draw this, so if I'm trying to draw the shape, if I'm trying to figure out where the atoms are, how many bonds they have, I need to know how many valence electrons I have to play with. So to count your valence electrons, you're going to use a formula pretty much. It's number of atoms multiplied by the valence electrons. So you're going to apply that to every atom, every element in that compound. Okay, so I like to make a list. So I would put, okay, the two elements that are combined here, arsenic and hydrogen. And I need to know how many atoms of each I have and how many valence electrons I have. So for arsenic, how many atoms do I have? And you're looking at the subscript.
33.
Not at the, you're looking at the atomic number.
Oh.
That's the number of protons.
Okay.
We want to know the number of atoms, so the chemical formula tells us the number of atoms. The subscripts are how many. So since arsenic didn't have a subscript, we assume there's just one arsenic atom in this compound.
Okay.
So we have just one atom, and we want to multiply that then by the number of valence electrons.
All right.
5, because it's in group 15. We do the same for hydrogen. We use the subscript to figure out how many atoms.
3.
3. And then the periodic table to figure out how many valence electrons. Just one. And then we need to add that. So the total, we multiply across and add. So we have 5, 3, for a total of 8. So we're going to use that number when we start drawing the structures. But before we get into more steps, let's practice this again. So going to C2H2CO2, if I wanted to know just the valence electrons in it, and this is a question you might have on the test. I might just give you a compound and say how many total valence electrons, and you would have to just do these steps to figure it out. So we have 2 carbons,
4 valence electrons.
4 valence electrons.
Hydrogen is 2 times 1.
1 valence electron. Good. So there's 2 of each element, so that's where those numbers came from, and these were based off where they are on the periodic table. We have 2 times 4 is 8. 2 electrons coming from hydrogen.
24.
14 coming from the chlorine for a total of 24, you said? All right. So the reason we're doing this, the reason we're trying to figure out the total valence electrons is because we're going to spread these out to figure out the shape. We're going to try to make everybody happy with that 24. Let's do this last one now. So we have hydrogen with a 3 by it, so that means
3
atoms.
Hydrogen was +1.
So we're looking at valence electrons, so it's a +1 because it has 1 valence electron. Yep. And then phosphorus, how many phosphorus atoms are there?
1.
Just one. If there's no number, you just assume it's one. And it's in group 15, so it has 5 valence electrons.
Oxygen has 4.
4 atoms,
And it is in 6 valence.
6 valence electrons. Right, so 4 atoms from the chemical formula, the 6 valence electrons because it's in group 16. 3, 5, 24.
32.
So 32 total. All right. So let's bring this to the next step. So let's look at drawing Lewis structures. So this is a compounds. And we're going to mainly focus on covalent. We're not really going to look at ionic because Lewis structures, we're usually showing bonds, single bonds, double bonds, triple bonds, and that's when electrons are shared. And covalent is sharing. With ionic, a lot of times, that separation of charge. You have a plus ion and a minus ion. So it wouldn't really be helpful for that. So we're going to start by just looking at this handout and the steps. So when you are approaching a problem, so let's do CO2. I have a list of steps, and you can switch these steps around if you want to. It depends on your preference. So generally the first step people do is they draw the skeletal structure of it. So what that means, they draw the arrangement of atoms. Where's the carbon, where are the oxygen? Who's central? Okay, so to figure out who's central, you're looking at the least electronegative atom that's going to be central. So you can use your electronegativity tables to figure that out, but a shortcut is, usually it's the first atom present. That's usually the least electronegative one. So you can just assume that carbon's going to be center. If you're not sure, or if you want to prove that, check and compare carbon's electronegativity to oxygen's. And you'll see carbon's is less. So what that means is I would put carbon in the middle. Then notice I have 2 oxygens. So I'm going to put an oxygen on either side because I just decided carbon was center. So that means I'm going to have 1 oxygen on either side. I'm not going to do this because this puts oxygen in the center, and I just said the least electronegative atom has to be in the center. Okay, so that's how you can figure out that this would be the correct connectivity of that molecule. Once you have the basic shape, you need to figure out the valence electrons, what we just did over here. Because we need to know how many electrons we have to deal with. So, counting the number of valence electrons, we make our list. We have carbon, we have oxygen. We look at the number of atoms of each and multiply it by the valence electrons. 1 atom, 4 valence electrons. Oxygen has 2, because that's subscript of 2. And 6 valence electrons. So 12 plus 4, right? So I have 16 total valence electrons. All right. So once I have all of my electrons, now I can start figuring out what it looks like. So how do we do that? We're trying to make everyone happy. So the reason the elements combine together is because they're trying to fill their octet. They're trying to get 8 electrons. So since this is a neutral compound, we're going to make sure everyone has 8. But first, we need to know what these lines mean. So every time you have just one line, this is a single bond, and it's going to be worth 2 electrons. So what that means is, if I drew carbon's Lewis dot structure, it would have 4 valence electrons like we saw here, right? Then say we have oxygen. Oxygen we said has 6. So 1, 2, 3, 4, 5, 6. So this line, this single bond, is because carbon and oxygen, they're sharing and making a bond with those 2 electrons. Okay, so that's the 2 electrons here, for instance. So we have 2 electrons here, but we also have a single bond on the other side because of the other oxygen. They're doing the same thing. So this is 2 electrons. So what that means is I've used 4 of the 16 I have available to me. The reason I figured out the total is I need to know how many do I have available to make everyone happy. I have 16 available, I've used 4 of them. So what do you do next? Well, next, your goal is to make the outer, the terminal atoms happy first. What that means is I'm going to put electrons around them, so dots representing electrons, so that they have 8 total. So this oxygen, it has 2 because it's sharing. So both of those electrons are belonging to oxygen, but they're also belonging to carbon. So since oxygen has 2, I want it to have 8. So how many more do I need to add to it? 6. And I'm going to put them in pairs, just like when we draw the Lewis structure. So now, it's 2 electrons, 4 electrons, 6 electrons, and that single bond makes it 8. So this oxygen is happy. I'm done with that guy. But now I want to make the next oxygen happy, the next terminal atom. We're worrying about the central atom last. So I'm also going to do the same thing, because it wants 8 as well. 2, 4, 6, 8. So now this oxygen has 8. So before I go and make the central atom happy, I need to look and see, do I have any extra electrons to put on him or not? So how many have we used? That's what we need to count next. So we've used 2, 4, 6, 8, 10, 12, 14, 16. So I've used all 16. What that means is I can't just go and add electrons on carbon to make him happy because I don't have any more electrons to put on him. How many electrons does carbon have right now? 2 from this bond and 2 from that bond. So carbon has 4 total right now, but he wants 8. And I just said we can't put electrons on him because we don't have any more to give. So what our next step is, when you look at the steps on this handout, it says number 6, the last step. If the central atom lacks an octet, so if it doesn't have 8, you can move 1 or more lone pairs from an outer atom to make a double or triple bond. So what it means by lone pair, this set of 2 electrons, this is a lone pair. So what we can do is we can take this lone pair and put it here to make a single bond, which will make this a double, right? So we said a single bond is 2 electrons. Well, now we're going to put this electron pair here, so draw another line. Now we have a double bond. And a double bond is 4 electrons, 2 and 2. So this is going to look like double here, and then we have this oxygen no longer has a pair up here because it's sharing that pair. Now looking at it, is carbon happy now? Does he have 8? No, he has 6. So we can go and have either this oxygen share to make a triple, or this oxygen share to make a double. And what the preference is, you always make a double before a triple. And that's due to bond energies. And this is in the PowerPoint when I talk about bond energies a little bit. We have single bonds are the least energy, then double, then triple. So since triple's the highest energy, that just means it's really hard to make. And they don't want to do what's hard, they want to do the easiest route. So we're going to make the double on this side, so this oxygen's going to share, to avoid making the triple, to avoid that high energy triple bond. So then we now have double bond to oxygen, double bond to oxygen. We got this here, and then this here. Okay, so this is the correct Lewis structure. I always like to, at the end, check and make sure everybody's still got 8. So oxygen has 2 and 4, 6, 8, because that's a double bond, so it counts as 4 electrons. Carbon, 2, 4, 6, 8, good. This oxygen, 2, 4, 6, 8. So everyone has 8, everyone's happy, that's the correct structure. Questions so far?
Not
A lot of steps, but
yeah.
try it out.
Catching up.
Oh, I put my good marker in with this set. I'm not gonna know what one it is. All right, which one do I have next? NH3, all right. We're starting off with, where we just have one central atom. We'll get into more complicated ones, but we want to get the hang of it first, hang of the steps. NH3, so you could choose to count the valence electrons first, or you could choose to arrange the atoms first, see what's connected to what. The steps on the sheet say to draw the skeletal structure first. So which element do you think should be central?
Nitrogen.
Nitrogen, yes. It's the first one, it's the least electronegative. So then that means these 3 hydrogens are going to go all around nitrogen. All right? So let's count our valence electrons. We have nitrogen, we have hydrogen, we need to know the atoms of each and the valence electrons of each. So that number of atoms, we look at the chemical formula. So nitrogen, just 1. Valence electrons, we look at the periodic table. 5 for nitrogen.
Hydrogen is
3 atoms. And valence electrons,
1.
just 1. 8 total valence electrons. Okay, so now we're already hitting our first exception. So we have the skeletal structure. Our goal is then to make the terminal atoms happy first. And we said over here, the oxygens want 8. But we're not dealing with oxygen anymore. We're dealing with hydrogen. How many valence electrons does hydrogen want?
2.
He just wants 2. Hydrogen was the exception to the octet rule. Hydrogen and helium, they only want 2. So when I go to make the terminal atoms, the hydrogen's happy in this case, they just want 2. And these lines, these are single bonds, representing 2 electrons. So each hydrogen already has 2. So they're happy. So that step's done. So now what I need to do, now that the terminal atoms are happy, is I'm going to look at the central atom. Nitrogen isn't, like the rest of them, wants 8. How many does nitrogen have right now with these single bonds?
6.
6 valence electrons. So we've used a total of 6. So we go over here and we say, okay, we have 8 to play with and we've used 6. So I'm just going to subtract 8 from 6. So how many do I have left?
2.
I have 2 left to play with. What that means is, since I have extra, instead of making a double, triple, whatever bond, I can just take these 2 and put them as an electron pair on nitrogen. So what that does is nitrogen now has 2, 4, 6, 8. So you want to put electron pairs if you can. The only time you're going to do a double or triple bond is if you don't have any left. Because that's what we did here. We said, oh, we've already used all 16, but carbon's not happy, so that's when you resort to double or triple bonds. But you want to stay at single if you can, because they're lowest in energy. So this is the correct Lewis structure. We used 2, 4, 6, 8. Nitrogen has 8. The hydrogens have 2. Everybody's happy. All right.
So did we use the dots because if we would have used another line, then that would have meant that hydrogen would have been off balance because it would have connected?
Say that again?
Like, did we use the dots on top of nitrogen? Cause a single bond equals 2, right? And we didn't use the single bond, just a line, because then it would have connected hydrogen and nitrogen and would have made hydrogen have 4. Hydrogen have 4.
Oh, so that's why we didn't want to do this?
Yeah.
Okay, so we don't want to do this for 2 reasons. One, hydrogen can't do a double bond like you just said because it can only have 2. So we couldn't have done a double bond. But also, you don't want to do a double bond if you don't have to, because single bonds are less in energy.
Okay.
So if you have extras, you do a pair instead of doing a double.
Okay.
All right, so with this structure, this is a tricky one. So the first step, sketching it. It says the least electronegative atom is central, and it's usually the first in the formula, not always. But notice the second bullet point. It says hydrogen and halogens are usually terminal positions. So we will not see hydrogen be a central atom. It can't be because it can only have 2 electrons. It can only have 1 single bond. If it was central, I'd have to have more than that. So here you see hydrogen and you might think, oh, that's the central atom, it's the first one. No, hydrogen is not central. So when this happens, go to the next one in the order, in this case carbon, and carbon is going to be the central. Hydrogen cannot be the central. So carbon's the central, and that means I'm going to have hydrogen on one side, nitrogen on the other side. Now I need my total valence electrons. My list, hydrogen, carbon, nitrogen, 1 of each. There's no subscripts, so that means there's just 1. Hydrogen has 1 valence electron, it's in group 1. Carbon has 4. And nitrogen in group 15 has 5. 5, 6, 7, 8, 9. All right, so that means I have 10. So when I'm done, I should only have 10 electrons in this structure. When I start distributing these electrons, I make the terminal atoms happy first. I worry about the central atom last. So starting with hydrogen, is hydrogen happy?
Yes.
Yes, so we're not going to put anything extra on him. He has 2 electrons with that single bond, he's good. Nitrogen, is he happy?
No.
No, how many does he have?
2.
Just 2 electrons from that single bond. So to make him happy, how many more does he need?
6.
6. So I'm going to put 2, 4, 6 on him. All right, so now we have the terminal atoms are happy, so I can worry about my central guy. So I'm going to look and I'm going to see, do I have extra ones to put on him? Because I would rather put electrons on him than have to make a double bond. So let's count how many we used. 2, 4, 6, 8, 10. So I've only have 10 to use and I've already used them. So that means I have no dots that I can put anywhere else. So now's when I have to do double or triple. So how many does carbon have right now?
4.
4, 2 and 4, both from the single bonds. He wants 8, so I'm going to have to take an electron pair from nitrogen and have him share. And what that does is it gives me a double bond here, and now nitrogen has 2 lone pairs instead. Okay, but is carbon happy?
No, 2, 4, 6.
2, 4, 6. So what do I have to do next?
Get another one.
I'm going to have to do another one because hydrogen can't make a double bond, so I have to do a triple. So then I get H, C, N, and then the nitrogen just has 1 lone pair left. It used 2 of its lone pairs to make the triple bond. So we have, let's make sure we still have the 10 total that we could use. 2, 4, 6, 8, 10. So it still has 10 electrons. Hydrogen's happy with 2. Carbon has 2, 4, 6, 8. He's good. Nitrogen has 2, 4, 6, 8. So everyone's happy, that's the correct structure. point something out. I see it over here as well. So why did I teach you about the Lewis dot structures? Because they can help you predict how many bonds the nonmetals will make. So nitrogen, 5 valence electrons. So this would be its electron dot structure, right? So it's non-paired electrons, that's how many bonds it wants to make. So that means nitrogen wants to make 3 bonds when it's in a covalent bond. And notice it has 3 bonds in this triple bond. And a lone pair on it, just like here. Over here, same thing. Except for to make its 3 bonds this time, it made 3 single bonds and a lone pair. So you can kind of expect almost all the time when you have nitrogen, it's going to have a lone pair on it. And probably 3 bonds, either a double and a single, a triple like over there, 3 singles, any combination of those. Carbon, we can look at that the same way. So if I do carbon, how many valence electrons? We said 4. So it has 4 unpaired. So that means we're going to see carbon make 4 bonds. So we probably will never see carbon with a lone pair on it for that reason. Because its Lewis dot structure doesn't have a lone pair. Like nitrogen does, so we expect it to have a lone pair in the structures as well. So 4 bonds, and then I don't have another carbon example, but we'll see this trend as we go. So, should we try a harder one?
Sure.
Well, we can do more of these ones before. Well, let's do the, well, arsenic's is going to be just like that, so never mind, I don't want to do that one. Sulfur. Oh, I don't know what to do. CCl4. If we wanted to name this, because we can now, it would be carbon, and then it's a covalent bond. So we're using prefixes. So it would be carbon. And I'm not saying monocarbon because it's the first element present, we don't use mono. Tetra because there's 4, and then chlorine becomes chloride. So by the end, you're going to be able to take a chemical formula and do all sorts of things with it. You can name it, you can draw it, you can figure out its shape, its valence electrons, everything. All right, so now we got that short review out of the way. Let's look at which one's the central atom then?
Carbon.
Carbon, first one. So that means all 4 of those chlorines are going to be around carbon. And part of the reason I know this as well is because I wouldn't want to do this. Because I have chlorine, a halogen, as a central atom. Carbon's a central atom, but so is chlorine, and it's not supposed to be. It says that on your sheet. It says halogens are not central atoms. Okay, so that's another reason why I know it wouldn't be that way. Okay, so let's count our valence electrons. So we need to know the number of atoms and multiply it by the valence electrons. So I have carbon, I have chlorine. I have just 1 and 4 chlorines. What is carbon? 4?
4. And chlorine is 7.
Chlorine is 7, just like all the other halogens. 28 plus 4, 32. So we're 2. So when all is said and done, this guy is going to have 32, so quite a bit. Now we've already used, because these are single bonds, 2, 4, 6, 8. We've already used 8. All right, so make the terminal atoms happy first. So each chlorine just has how many electrons with that single bond? 2, so it needs how many more?
6.
6, because it wants 8. So I'm just going to go around and do that to every single one. It's a lot of dots. Okay, so now my chlorines are happy. Is my carbon happy?
2, 4, 6, 8, yep.
So he's happy too, okay? So my next step is just to check and count all my electrons to make sure I didn't go over the 32, or to make sure I don't have any extras. So 2, 4, 6, 8, so there's 8 times 4 is 32. So yes, I've used exactly 32. Everyone's happy. That's the correct structure.
Okay, cool. I think I got it now.
And to bring it back to the Lewis dot structures, we said carbon forms 4 bonds, in this case 4 singles. Chlorine, when you look at that Lewis dot structure, how many valence electrons does chlorine have? 7. So that means it's going to have just 1 unpaired electron. So it's going to form 1 bond. So that's another reason why we wouldn't see this structure here, is because since chlorine just has 1 unpaired, it usually just forms 1 bond, and in this diagram it would have 2 bonds. So you'll usually see chlorine with just a single bond and then 3 electron pairs around it, just like in the Lewis dot structure. So, awesome, that was a good start. So what we'll look at next time is we'll do more complex ones. So we'll start doing ones with more than 1 central atom, and then we're going to look at ions. So all those polyatomic ions that we talked about in the last part of the chapter, those are covalently bound, so we can actually draw the Lewis structures of those as well.